Hello guys, I am Saurabh Gupta. I am a student of IIT Bombay and currently I am studying mechanical engineering. I have returned my JEE in the year 2010 and secured an AIR of 443. And today we are going to discuss something about alkyl halides and aryl halides. This is the advanced level of this topic, and so therefore you are supposed to go through all the topics, all the reactions, all the mechanisms, substitution reactions, elimination reactions, all the theory before starting this lecture. You can refer either NCERT book or any other standard textbook, or you can go through the basic lecture also. So today what we will be doing is, we will be doing some questions based on the reactions we have learned in the basic lecture. That is, we will be doing some questions based on SN1, SN2, E1, E2 and the nucleophilic aromatic substitution. So let us start one by one. There will be a variety of questions in this lecture. You will find that the pattern of J is quite similar to what we are going to discuss. So the first question is, the best method to prepare neopentane. So the best method to prepare neopentane is option A, CH3 thrice CCH2OH. So the reagents given to you are PCl5 upon heating, HCl upon heating, SOCl2 upon heating and in presence of pyridine, and finally chlorination upon heating. So these are actually the four options given to you. The reactant is the same. Either you have to use this reagent, this reagent, this reagent, or the finally Cl2 and light. Fine. Now the best method to prepare neopentane from an alcohol. So that alcohol suggests that neopentyl chloride, not neopentane. This reagents won't give you neopentane, it is neopentyl chloride. Yes, we have an alcohol and we are supposed to prepare a chloride. Now if you remember the preparation reactions of chloride, then you can easily do this question. And not only remember the reactions, but also what are the limitations, what are the advantages, etc., etc. And even if you don't remember, you can just write the reactions or the mechanisms for all these three, and then we can see what is the correct answer. So writing the complete structure, CCH3 thrice CCH2OH, PCl5, HCl heat, SO2 heat and pyridine. All of them, what is the mechanism followed? The mechanism which is followed is, they all follow SN1 mechanism. Now you would ask, SOCl2 pyridine is not exactly SOCl2, as I have explained in the basic lecture. When it is reacted with an alcohol, it is not exactly SN1. The retention of configuration is taking place and there is no rearrangement. But remember, I have added one more reagent to it, that is now the solvent is pyridine. So that means there will be some difference in the reactions. Let us see first that itself. SOCl2 heat and pyridine. So that gives us a polar solvent. Pyridine is a polar solvent. Pyridine is this. Pyridine is same as benzene except for the fact that you have replaced one carbon atom with one nitrogen atom. Fine. Now in presence of this solvent, how does SOCl2 react with that alcohol? Now in fact, in presence of pyridine, this follows an SN1 mechanism. That means formation of a carbocation takes place. But this does not happen when pyridine is not present. Why? Here comes the effect of solvent. If you remember, we have discussed the factors which affect the nucleophilic substitution, and one major important factor was the effect of solvent. So what is the effect of solvent here is, formation of carbocation takes place from this reactant and pyridine exactly stabilizes the carbocation. How does it stabilize? Pyridine has got a lone pair of electrons. So hence it can happily donate the lone pairs of electron to the carbocation, and hence it can stabilize it. While if the pyridine is not present, the carbocation is left open to anything and it is not stabilized at all. So that is why in presence of pyridine it follows a carbocation intermediate. While if pyridine is not present, we have already discussed what is the mechanism, and it happens with the retention of configuration. It is a pseudo SN2 reaction which happens with the retention of configuration. Fine. So let us write the mechanism. CH3, 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 C positive. So the alcohol will be protonated, will be gone as OH2 plus, and the positive charge will come on the carbon. Fine. Now this actually undergoes rearrangement. We know it is a primary cation. So that means this will undergo rearrangement and we would get CH3 carbon, and the rearrangement happens to here with the migration of this CH3. First this hydrate shift occurs so that it becomes a secondary carbocation. First, due to the hydrate shift it becomes a secondary carbocation, and then through this methyl shift it becomes a tertiary carbocation. So finally what we get is this kind of structure, CH3, CH3. We have actually done a mistake that this carbon we have added extra. I'm sorry, this carbon we have added extra because there are 6 carbons in this, although we are talking about only 5 carbons. That is only this bond, and hence now it happens like this is the positive charge, and now there is only one rearrangement which is required, which looks something like this, or otherwise you can write this CH3 on this side also. Fine. So we have got our stable carbocation, and now the final step, that is Cl minus comes and attacks at this carbon, and it is a planar carbon, so we will get 2 isomers, that is 2 enantiomers of these 2 carbons. Actually we will not get, because this carbon does not become chiral when the Cl minus attacks. So that means we have only one kind of product, that is this product. But what is this product? Is this a product we want? We wanted neopentyl chloride. The structure of neopentyl chloride is C, 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 and the Cl should be attached at this terminal carbon and not to the middle carbon. But here you see the CH3 has shifted and the Cl has attacked over here. So that means this is not the product which we want. And similarly with PCl5 and HCl heat, you will observe that we will get same product. Why? Because all of them follow the carbocation intermediate path. So that means none of them give us the major product isopentyl chloride, neopentyl chloride. But what about this reaction, Cl2 and H nu? If we have the Cl2 and H nu, what is this reaction? We can quickly recognize that this is a free radical reaction. That is, what we have here is C, I can just shorten this bond, C and OH, and we have Cl2 and H nu. So what is the possible product over here? Now this reaction will again give us a chloride, but with a different mechanism. This follows a free radical mechanism. That means the free radical, the product, the option is not this, the option is that we have a pentane, we have isopentane. In these three we had an alcohol, neopentyl alcohol, but here the option says we have neopentane. Fine. Now if you recognize this reaction, it is the halogenation of alkanes, and halogenation of alkanes proceeds through the what? Free radical mechanism, and free radicals do not rearrange. This is a very important property of free radicals, that they do not rearrange. Yes, they are stabilized by resonance, but they do not rearrange. That is, methyl shift doesn't occur there, so that you can get a tertiary free radical. And that is the advantage we take, and this Cl will be added over here, and hence we get our neopentyl chloride happily. So this question is a very nice question. There is a very cute concept involved in this, that although carbocations rearrange, free radicals do not rearrange. So that was it. This was the first question. Now let us move on to the next question. So the best method for the preparation of neopentyl chloride is take neopentane and do chlorination in presence of light. Fine. Now the next question is a subjective one, and you have to answer it quickly. I will give you a reactant and I will ask you what are the possible products. The question says this compound CH3Br, when it is reacted with CH3OH, you get A plus B plus C plus D plus E. Fine. Now we have quite a good number of products, that this reactant reacts with this reagent and giving us some good number of products. So obviously the question is identify A, B, C and D and explain their mechanisms. Fine. Let us see what are the possible reactions. Now we have an alkyl halide and we have got an alcohol here, which is a methyl alcohol, and so we have got a nucleophile. We know this is RO minus, which is a very good nucleophile. Now RO minus can also act as a base. So that is a very important part, that this can play the role of a nucleophile as well as a base. So that means E1 as well as E2 as well as SN1 as well as SN2 reactions are possible. But we have got 5 products and only 4 pathways. That means where is the 5th product coming from? Let us see. So first going for the E1 mechanism. Now if you take E1 mechanism, we get the first step in E1 mechanism is that the halide leaves. So it is dehydrohalogenation and the halide simply leaves. And there is obviously a hydrogen over here. So dehydrohalogenation is possible. We get this sort of carbocation. Now carbocation stability. The stability says that this has to rearrange. And how can it rearrange? If this carbon donates its bond pair to this carbon and it donates its lone pair to this carbon. So now we get a 6-membered ring and a positive charge somewhere here. Fine. So this is our stable carbocation which has rearranged, and we have got this. Now next the final step is that you get an alkene. You can get any alkene, both the alkenes are equally stable. Fine. So let it be our product A. So this is our product A. Now another mechanism can be the E2 mechanism. In the E2 mechanism, what happens here is that this Br and this hydrogen which is present over here, there is exactly one hydrogen. So this Br has to go in such a position such that this hydrogen and that Br are anti to each other and they are coplanar, and definitely this is a single bond, so the carbon can rotate and we can definitely get that configuration. So definitely E2 mechanism is possible. Fine. So if E2 mechanism is possible, we know what is the product in that case. There are no rearrangements and there is only one hydrogen to dehydrogenate form, so there is only one product possible. So let this be product number B. Let me write it with green so that we can distinguish between the answers. Fine. This was the E1 mechanism and the E2 mechanisms. Now what about nucleophilicity? We can have SN1 as well as SN2 reactions. So let us see SN1. SN1 reaction, let me write it with black. That is much better. SN1 reaction, what is the first step? First step is same as that of E1, that you get a carbocation. And where exactly do you get a carbocation? You get a carbocation at the same place as you get in E1. That is, the alkyl halide just leaves. So that means the first step is same in SN1 and E1. So directly I am writing the rearranged carbocation, that is this. Now what happens? Now this bromine comes and attacks over here. Sorry, this OCH3 comes and attacks over here. So this on OCH3 minus gives you a product like this. And tell me whether you will get a racemic mixture or not. You don't get anything. You will get a single product because this carbon is not chiral. There is a plane of symmetry in this case. So we will take OH3 and we will add it over here. OCH3 and we will add it over here. Fine. What about SN2 mechanisms? Let us write SN2. SN2 is what? SN2, we will eliminate, we will have to substitute this Br with this OCH3 simultaneously. Okay, so let us do it. And in SN2 what happens is the carbon configuration changes. That is, this 3CH3 will be on this side, but still that does not change any R or S nomenclature because that carbon is not chiral. So we get C, we get 3 hydrogens this way, and we get an OCH3. No need to mention Br is a leaving group, OCH3 is a nucleophile. Fine. So what we have here? We have here 1, 2, 3, 4 compounds. This is, let it be our C, and this let it be our D. Now what other reaction do you think is possible over here? We have alkyl halide, we have an alcohol which can act as a nucleophile. What else? Elimination is over, substitution is over, but what else? Nothing else actually. There is no other reaction possible, but yes, there is one more product possible, although a very, very minor product. And can you see from all these reactions which is that product? Yes, you are right, that it is from this. If this carbocation does not rearrange, what happens? If this carbocation does not rearrange, then we have this kind of product. This carbocation and we have this. But you will say again, carbocation is not rearranging, and then you can abstract this hydrogen with this E1 and we will get this alkene. So where is the fifth product? Fine. You are right about this, but think a little bit more. Yes, that could have also given a different product. That if this ring expansion was not happening, that could have also given a different product. But still, there is one place where you can get a different kind of a product. There is, suppose in SN1 case, if you don't rearrange the carbocation like this, you arrange the carbocation in this way. This is correct, but this is a carbocation C plus, and you just do a hydrate shift over here. That is, this becomes CH3 and this becomes a carbocation over here. Now what do you get? Now what you get is, you get a OCH3 over here. Fine. This becomes our fifth product, which is E. Now you can ask, why didn't I do the same thing in this case? Yes, I could have done that thing in this case, but what happens here is that we are asked only 5 products and we have got 5 distinct products. If we are asked 6 products, then we could have taken this case also and we could have got something like this and this. This is a quite stable alkene also. But this reaction is more feasible than that reaction, because in this case the energy barrier is lesser as compared to the elimination reactions. So that is why we can also follow a higher energy path and still get a very stable product as compared to the elimination one. So that is the difference. So here the difference is the energy of the elimination and the substitution reactions. So very nice question, but the carbocation can become stable either through ring expansion or either through the hydride shift. Both gives us a more stable carbocation as compared to the previous one. So two simple logics, but a very nice question. Fine, let's move on to the next question. The next question again is based on elimination and substitution reactions. So let us do it. There are 4 options, there are 4 questions, and obviously you have to write the products for all the 4 reactions. The first one is CBr CH3. The reagent is Ki acetone. Fine. The second one is CBr CH3 and we have KOH plus C2H5OH and heat. Fine. Let's consider these two first. Here we have got the same reactant but 2 different reagents. So what are the possible products? Possible, we have tried either the major product or the major products. There are infinite possible products, but we are supposed to write the major one. Fine. Here in this case, Ki acetone is there, and do you recall this reaction? This is actually the displacement of one halogen by the other. Here the iodine is displacing bromine. But how is that a very feasible reaction? Because of the presence of acetone over here. Because the acetone is present, what it does is, this will tend to move the reaction in the forward direction. We have already discussed the reasons in detail. So we can directly write the product, which is iodine. Fine. What about the second case? What is the possible product over here? First of all, try to recognize what is the reaction. We have an alkyl halide, so that means in one of the properties of the alkyl halide. And we have KOH and C2H5OH. Now this one gives us, we know, a nucleophile C2H5O minus. So that means substitution reactions are possible. Definitely, it is a secondary halide. Substitution and elimination both are possible. But which one to choose? We know that if it is not a very bulky base, even if it is a bulky base, this higher temperature gives us a clue that this must be an elimination reaction. If the higher temperature was not there, then the substitution would have been also a very equivalent major product. But if we take a bulky base over here, then definitely, even if you don't provide heat, the major product is the elimination product. We have discussed all this when we were discussing difference between substitution and elimination. So this product we can easily write CH3 and CH3Br. Now here, what do you think is the pathway? E1 mechanism or E2 mechanism? Whether it is E1 mechanism or E2 mechanism, the product is going to be the same, so don't bother about that. But what is the probable mechanism? Both are actually equally possible. The secondary carbocation is good enough and there is not much of overcrowding because the base is small enough. So that is why we can have both E1 or E2 and we get a product which is this double bond C. The bromine and one of these hydrogens. In this case, I have eliminated that HBr group, and this is dehydrohalogenation, which gives us an alkene. So remember this heat. Let us now consider the next two set of reactions. The next two set of reactions also will tell us and will guide us correctly to understand in depth the knowledge of difference between substitution and elimination reactions. Let us see what the two reactions say. We have CH3, we have Cl, we have CH3, and we have CH3O minus Na, and we have CH3OH. Fine. The next product, the next reactant is CH3Br, CH3, CH3, and we have this CH3 thrice, CO minus, K plus. That's it. So what are the possible products over here? Again, clearly this is the dehydrohalogenation case, and you must get a alkene. Is it really? Why can substitution take place? Yes, definitely substitution can take place. There is no doubt about it. So let us again consider the factors which favor substitution and elimination. This is a tertiary halide. So that means substitution is a very difficult possibility, and elimination is a more favorable one because this is a strong enough base, and we can get a stable carbocation and we can get a stable alkene also. But the thing is, why do you think these two are asked like this? Because these two are asked together, it makes us think like here we must write the substitution product, and here definitely it must be the elimination one. Why? Because this is a bulky base, and with bulky bases the tertiary halides will give only elimination products, because already this tertiary halide is bulky. If you make the base bulky, then the nucleophilic attack becomes very, very difficult, and hence even if you go by SN1, the base has to approach the carbocation, and that approach becomes very difficult if the base is bulky. That is why elimination is best preferred, because in that case you have to abstract only a terminal hydrogen. Fine. So this is definitely elimination product, but this thing here mostly you will be thinking elimination product only, but here that heat factor is missing. They have not provided us heat. If they were to write, because this is a very confusing case, you have equal probability of elimination as well as substitution. Substitution, why? Because the base is not bulky. Even though this is sterically hindered, but you know what happens in SN1 or even in SN2. SN2 is definitely not possible. This is very bulky. SN1 case, it is like positive charge, and you can have the attack of the nucleophile because the nucleophile is small. So, I mean, both are possible, but since here elimination is coming, mostly they will be asking the substitution case. And don't apply your logic like this. There is one more reason why I am saying that. See this chlorine and see this bromine. Tell me the livability is more for what? Clearly it is bromine, and hence the chlorine won't leave so much easily. So that means if you go through the SN2 pathway, what happens is that these three CH3 groups face the back side, or it becomes planar, and CH3O minus comes and attacks. So that also gives us a clue that here we must write the major product as the substitution one, and here the elimination one. So if we write the substitution product over here, we can just write CH3, CH3 and CH3, OCH3, CH3. Here if you want to write the elimination product, remember this is a bulky base, so we will be abstracting a hydrogen from these. And anyway, the middle carbon does not contain any hydrogen, but this carbon also contains the hydrogens. So that means we get a carbocation, CH3, CH3, and we have CH3. Now we have hydrogens over here also, and we have hydrogens over here also. But since it is a bulky base, it won't go towards the stable alkene. It will go towards the Hofmann product, which is this. Fine. A very simple E2 reaction or E1 reaction in which we get a carbocation, and then because of the bulky base, the major product is the Hofmann product. Fine. This is the end of this question. Let us move on to the next question. The next question is, let us take this compound CH2 and treat it with the familiar reagent, that is NBS. And now you have to predict what is the, actually I am giving you 4 options, so that makes your job easier, and you have to choose the correct product from those 4. So this is the question number 4. First option, options, let me write it in blue. First option is, we have CH3 and here we have Br. Second option is, we have a Br on the double bond, something like this. Third option is, we have this kind of compound with Br and CH3 this way. Fourth option is, we have a double bond inside and CH2 Br. Fine. Now out of these 4, you have to select the correct option. So let us proceed with the logic. What is this reaction first of all? This reaction seems to be like a property of alkenes to react with NBS. And here, do you know what the product is? The product will be an allylic halide. Yes, we know that when you react an aniline with NBS, the product is generally the allylic halide. But if you find that type of structure over here, that means the bromine is either over here or over here with the double bond with outside the ring. You do not find it here at all. All you find is the most matching structure is this, but the double bond is missing from here. So what is the structure now? It is not available in the options. So what has happened to the answer? Let us try to find out. Let us try to write the mechanism for this reaction, so that actually we can get whether we are making some mistake or we are actually correct and the options are wrong. So what is the mechanism followed in SBS? The mechanism which is followed is a free radical mechanism. Yes, this is also an example of free radical mechanism. So let us try to write this free radical mechanism. First of all, think this NBS produces a bromine free radical. So if you have a bromine free radical, what is the possibility over here? That CH2, one free radical over here, but that can be taken as H, and one free radical over here actually creates a free radical over here, and directly bromine can come and attack over here because it has created a free radical there. Now that free radical is quite stable, although the rearrangement does not take place, which it cannot take place here either through a hydride shift. If you want to do a rearrangement, you have to do a hydride shift. But remember, for free radicals, rearrangements do not take place, and hence they are only just stabilized by resonance, nothing else. So if you write the resonance structures, a double bond comes over here and the free radical goes over that carbon. And now if you see the second resonance structure and combine this bromine free radical with that, so we get a CBr bond which is in conjugation with the double bond. So what do you observe? The option 4 actually matches with that. And why is it so? Why is this the major product and not this? If Br comes over here, then this will be our major product. I mean, why it is not this major, this is a major product and not this. The reason is, see the stability of the alkene which we have formed. Here the major driving force is the Sergev rule, which says that more stable alkene is formed. Although Sergev rule is given only for even mechanism, but we can apply it anywhere because our aim is to get a more stable product. So if you see, this is definitely more stable than this alkene, and hence our major product becomes this, and our correct answer is the fourth option. So in fact we were also right, the options are also right, except for the fact that we didn't write the mechanism. We just blindly wrote what is the only possible product. We didn't check for the other possibility, but once you write the mechanism, it becomes quite evident that this is also a possibility, and hence this can be the answer. Fine. Although there is not much difference between the stability of these two, so if this was also there in the option and that was also there in the option, then you can actually mark both because there is not much difference in the stability. But if they are specifically not giving this, then definitely you have to mark this. Fine, let us move on to the question number 5. The question number 5 says, it is a subjective question and you have to explain the formation of the product, and obviously you have to tell what the product is. I will just give you the reagent and the reactant. So question number 5 goes here. ROH alcohol plus a big reagent SiCH3, CH3 and CCH3 thrice. So quite a big reagent. We have an silicon atom, a chlorine atom attached to it, and we have some alkyl groups attached to it. Now what you are supposed to do is, you are supposed to predict what is the product A, and if you treat the product with Mg ether, what is the product B. Fine. Can you do this question? I mean, there is an alcohol, there is something which contains a chloride ion, you have to predict the product. So can you think of any reaction which is possible? Yes, I can think of this chlorine and this alcohol. We know that this is a nucleophile, it has got lone pair of electrons, and there is a good leaving group present on the silicon. This is simple example of an SN2 reaction, except for the fact that instead of carbon we have got a silicon. There is no other difference. If I just put a carbon there, immediately you can write the SN2 product. But if I put a silicon, you will come in doubt. So that doubt should not come, and you can actually write this, and this product becomes ROSiCH3, CH3 and CCH3 thrice. Fine. So that is our A product, a very simple SN2 reactant. Fine. What about B? Now B must be very easy for you because this kind of reagent comes in only one reaction, and that is a Grignard reagent. So Mg ether gives you RO minus R minus MgX. X in this case it is what? X is this part. This whole part is X right now. So I will just denote it by X only. So that is our X. So we have got a Grignard reagent. Instead of Rx, here we have taken a protecting group. That is, here this is called a protecting group. Why is it called a protecting group? Because if you directly take ROH plus some Mg ether like this, Mg ether, then in that case what happens is, you will get the Grignard reagent as Mg OH minus, no problem. But this R minus will immediately react with another molecule of ROH and will be destroyed, because we know R minus is a very strong base and it can abstract. This is a very acidic hydrogen. Even it can abstract the acetylene hydrogen. This hydrogen also can be abstracted by R minus. Then this is a very much acidic hydrogen as compared to this. So that is why you cannot prepare Grignard reagent through alcohols. And even suppose you consider this kind of carbon chain. I have a chlorine and alcohol both on the same carbon chain. Even the Grignard reagent cannot be prepared through this compound. Why? Because even if you are preparing Grignard reagent through this Cl, that will immediately react with this alcohol and give you, it will destroy your Grignard reagent. So there is no point in preparing Grignard reagent for those compounds. It cannot be prepared actually. It cannot be synthesized and it cannot be isolated. Even though this species, that Grignard reagent, might exist for some few milliseconds or nanoseconds, but the next moment it will react with the acidic hydrogen and will be destroyed. So Grignard reagent cannot be prepared with the compounds in which there are acidic hydrogen groups. NH2, sorry, not NH2, we have OH, we have some groups like CN, not CN, SH. So if it contains all these kind of groups, and also I told you C triple bond C, so if it contains a terminal alkyne, then also it cannot be prepared. So be very careful. If you are given Mg ether, just don't directly write the Grignard reagent. You have to be very careful, and we have to judge whether Grignard reagent could be prepared from this particular reaction or not. Fine, coming back to the question, we got our Grignard reagent, fine, but we know that ROH cannot give the Grignard reagent. So what we have done to get the Grignard reagent? What we have done is, we have replaced this hydrogen by this big group, which is called a protecting group. Now this group protects this hydrogen from being abstracted by the Grignard reagent. So that is why this group we have added, we have protected the hydrogen and we have performed our reaction and got our Grignard reagent. So this X is not right now the chloride. So how do you get it? How do you get a halide there? Because this X is now the big protecting group and not the halide, and that is not the Grignard reagent exactly. So what you need to do is treat it with any halide. Suppose CH4 plus and F minus. So this is a very strong halide which can displace this O bond and get connected to R. So then you get a perfect Grignard reagent. So that is why this question is very nice, because it shows you how you can prepare Grignard reagents through groups or in compounds where there is an active hydrogen or there is a very acidic hydrogen. You can protect the acidic hydrogen through this group, and then you can replace that group with some halides, suppose for example with F minus or Cl minus also, and get your Grignard reagent ready. Fine, this was a nice subjective question. Now let us see an assertion reasoning question. Assertion reasoning question, the most important point is you must read the instructions in the question paper before solving any question of assertion reasoning, because mostly they will change all the rules, A, B, C, D, different options and different meanings for this A, B, C, D. But right now we are going to just follow the normal rules, that A means that both the statements are true and it is the correct explanation of that, and B means it is not the correct explanation of that, and C and D accordingly, like it is C is the statement 2 is wrong and D is the statement 1 is wrong. Fine, so assertion reasoning. Statement 1. Statement 1 says benzyl bromide when kept in either acetone or water. This is not either acetone or water, this is a mixture of acetone and water. Acetone is quite soluble in water because it is a carbonyl compound, and as we will see that carbonyl compounds are quite soluble in water because of hydrogen bonding. The double bond O can form hydrogen bonds with the other water molecules. So benzyl bromide, when kept in acetone water, it produces benzyl alcohol. It produces benzyl alcohol. Benzyl alcohol. Statement 2 says that the reaction follows SN2 mechanism. Statement 2 says that SN2 mechanism. Fine. So let us find out what is the correct answer for this question, and for that we need to check the validity of both the statements one by one. Let us see whether the first statement is correct or not. Benzyl bromide. What is this benzyl bromide? Benzyl bromide is some compound which has a structure like this. Oh, I have done chloride. Benzyl bromide is this way. Fine. So this benzyl bromide, when kept in this mixture of acetone water, we get benzyl alcohol. Remember, this is not an aryl halide, this is a benzyl halide. And aryl halide, the properties are very much different from the benzyl halide. Benzyl halide just acts as a normal alkyl halide, except for the fact that if you go for SN1 mechanism, you get a very good stability for the carbocation because of the phenyl group. That's all. So don't confuse this with aryl halide and try to write some nucleophilic aromatic substitution product or something. This is a normal benzyl halide and it acts like a alkyl halide only. So the product which the question says should be benzyl alcohol. Is it right? First of all, I mean, water is there. Yeah, so water can act as a nucleophile and replace this Br. What is wrong in this? There is nothing wrong. But there is something wrong about statement 2, I feel. Statement 2 says that it follows an SN2 mechanism. Now here what happens is this H2O is obstructed by the electron cloud over the benzene. Because of the electron cloud that is so huge and this structure is quite small, CH2, that H2O has got some difficulty in approaching this carbon. So a better method would be if you can just leave this bromine, create a carbocation. Now in that case what happens is the H2O can come from the top or from the behind without any obstruction, and hence it can give the CH2OH. So according to me, the first statement is true and the second statement is false, because SN2 mechanism doesn't seem to me to be appropriate, but SN1 seems to be perfectly good because we get a very stable carbocation. Fine. So this was the assertion reasoning question, and finally what is the answer? Statement 2 is false, statement 1 is true. So we get the answer as C. Very simple question. Fine. Now let us do a difficult question. I am just telling you it is difficult, but don't believe me. It might be simple for you. So the next question says this. We have this kind of structure, this kind of molecule, C plus, and there are two groups. You have to tell that why this is lesser stable than CF3 plus. CF3 plus is seemingly more stable than the C plus and CF3 group and the two alkyl groups. Tell me, what is the possible reason why this is lesser stable as compared to this? While on the first side it seems that this toluene will have so much negative inductive effect that this carbocation will be unstable like hell. This is okay, let me draw proper carbocation. F, and then we have F here and a positive charge over here. Now you have to tell me what is the reason why this structure is more stable than this structure. There is so much inductive effect, and we know that inductive effect increases as the carbon comes closer. That means here the inductive effect is actually lesser, and here the negative inductive effect is actually more. But still this is more stable than this. Now there can be only one reason why it is more stable. It might be that the the 2p orbitals on F and the 2p orbitals on C, they have got the p pi bonding. Now this is an example of back bonding, which is the p pi bonding. That means F has got some amount of electrons, a good number of electrons, and carbocation is there. So if this carbocation can get some electrons from this F orbital, what is wrong? It will be stabilized. So each of this F contributes to this empty p orbital and makes this carbocation more stable as compared to this carbocation. And if you see in this carbocation, the inductive effect is there, although there might be some positive effect due to these groups, but there is no back bonding. And back bonding is very stabilizing factor, which can, what is the effect? CF3 plus is more stable than that carbocation. So this was a nice question, and this can actually have more applications. This question can be asked as more carbocation in even reaction, in SN1 reaction, because wherever carbocation is there, we can have a question on that. Carbocation stability determines the rate of reaction of even reaction, of SN1 reaction, so it is very important. So let us now see another question, which is based on nucleophilic aromatic substitution. I am giving you the clue now itself so that you don't complain later. The question is, there is a benzene ring, we have OCH3, we have bromine, we have CH3, and this is treated with KNH2 in liquid ammonia. This is just a solvent, and we have another compound, a similar compound, OCH3 and bromine over here. Fine. Okay. Now tell me, and this is also reacted with KNH2 and ammonia. I will be giving you 4 options, and you have to select the correct options from there. So first option is that first compound gives nucleophilic aromatic substitution, and the product is OCH3 Br CH3. Sorry, I have written the same compound. The product is NH2 over here. Second option is the second compound shows nucleophilic aromatic substitution and gives OCH3 and NH2. Then the third option is the first compound shows electrophilic aromatic substitution and this gives OCH3 NH2, sorry, Br CH3 Br CH3 and NH2. And fourth option is second compound gives electrophilic aromatic substitution and gives the following compound: OCH3 NH2 Br and NH2. Fine. So now you have got 4 options and you have got 2 compounds. You have to tell which of the 4 options are right. First option says that first compound shows nucleophilic aromatic substitution and gives this kind of compound. And the third option, the second and this is the third option says that first compound shows the electrophilic aromatic substitution. Now, first of all thing, what is this KNH2? KNH2 is a nucleophile because NH2 minus is a nucleophile. And what is this? This is definitely not an electrophile. This is also a nucleophile because it is a benzene ring, and benzene ring has got the pi electron density with it. So definitely this is not the nucleophile. This is not an electrophile. So how can reaction happen? I mean, you don't have electrophile, both are nucleophiles. So how will this electrophilic aromatic substitution happen? For electrophilic aromatic substitution, you need electrophile so that the nucleophile benzene can donate its pi electron cloud. So that means this is definitely a wrong option. So third, and similarly fourth is also a wrong option. Why? Because second, electrophilic aromatic substitution is definitely wrong. Electrophilic aromatic substitution, again in this case it is not possible at all. Why? Because both are nucleophile and you don't have any electrophile. So that means we can just remove these two from our list. Let us see what about the first and the second. Nucleophilic aromatic substitution is very much possible, and we have seen the mechanism of this reaction in the basic lecture. So now let us try to write the mechanism. OCH3 Br CH3, and we have double bonds this way. Fine. What is the first step in the mechanism? Side by side, let us write the mechanism for this also. We have OCH3 Br double bond double bond double bond, and here. What is the first step in the mechanism? The first step in the mechanism is the abstraction of a proton by NH2 minus. NH2 minus is a very strong base, so that is why it can abstract proton from this carbons as well. So which do you think proton will be abstracted? Which proton will be abstracted? So the proton that will be abstracted would be either this or this, because the proton has to be ortho, and moreover we will get the carbon ion, and that has to be also stabilized. But in this Br case, both these positions are occupied. One carbon position is occupied by OCH3 and hence there is no hydrogen, and here one position is occupied by CH3 and hence again there is no hydrogen. So the first step of the mechanism itself cannot take place, and you do not get nucleophilic aromatic substitution product in this case. But yes, there are two free positions and we will go with this free position. So now we will get a carbon ion over here, double bond over here, Br over here, and actually the thing is the carbon ion cannot come here, the carbon ion has to come over here. Carbon ion and Br. Fine. Now what happens next? Next what we get is the benzyne intermediate. So what we get after this step is that Br leaves and it takes away the electron density with itself, and this carbon donates its electron density into that carbon p orbital. So we get a product which is something like this. Now this is called the benzyne intermediate, and this intermediate is a very special intermediate because although it doesn't look aromatic, it is an aromatic intermediate and hence a very stable intermediate. So now what is the next step? Next step is obviously hit NH2 over here, OCH3 over here, and we have the hydrogen gone from here. So that's it, you get a hydrogen added to it actually. So that's it, we complete the mechanism and we get this kind of a product. So OCH3 NH2, OCH3 NH2. Now you can also have another kind of a product, that you can also get the para product from here. Why? Because the NH2 can either attack from here or you can attack from here. So there are two products possible. Fine. So this was a question on nucleophilic aromatic substitution. So now let us move on. It is a very important concept the nucleophilic aromatic substitution, because it is very recent, the discovery of nucleophilic aromatic substitution. Till now it was thought that benzene cannot undergo nucleophilic substitutions, it can only undergo electrophilic substitutions. And what is electrophilic substitutions? We have seen that in that one hydrogen is replaced by another group instead of our halide or something else. These nucleophilic substitutions are characteristics of aromatic halides. Let us do another nice question. Let us take this compound CH2N, a carbon, of bromine, and we have CH2OH. Now this is actually treated with a base. Now you have to tell me what is the product that is obtained. I will again give you 4 options and you have to choose which options are correct. So first product, if n equal to 1, then in that case the product is C O C CH2. One second. If n equals to 1, then in that case this CH2 won't come, because in that case we will have only 3 carbons and 3 carbons have already come. And second one, if n equals to 3, then what happens? If n equals to 3, then in that case we have carbon, carbon, oxygen, 3 carbon. We have 4 carbons, but we have 5 carbons over here, so that means it will be carbon, 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 oxygen, carbon. Fine. Second, if n equals to 2, the product is carbon, 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 oxygen, and fourth one is none of the above. And you can have a fifth option also, that C Br CH2N CH2 C CH2N CH2OH. Fine. So these are the 5 options given to you, 1, 2, 3, 4, and the fifth one is none of the above. Now which of the option or which option is correct? So this seems to be a very interesting question, because in the first 3 options there is no sign of Br, neither OH. Where have they gone? So let us find out where have they gone. If suppose n equal to 1, then let us see what is the product. So if n equals to 1, then we have Br CH2N CH2OH. We are treating it with a base. What does a base do? A base abstracts the acidic hydrogen from a molecule. So base, then the only acidic hydrogen available is, okay, these are also acidic, but the most acidic hydrogen which is available is this hydrogen, Br CH2 CH2O minus. Now next, what is the next step over here? The next step over here is, we have a halide over here. So what it can do is, it can combine with some other molecule of the same kind. So suppose this is the second molecule, then this comes and attacks this carbon, Br leaves, and you get one carbon, CH2 CH2OH. So something like this product if n equals 1. So that means this is not a correct option, because n equal to 1, it suggests some cyclic kind of structure in which there are 3 carbons and 1 oxygen. So our correct answer must be the fourth one. because this suggests this kind of structure Br, C, CH, CH2, C, C, COH. Fine. So this is the one of the correct options, or maybe the only correct option. Let us see the other options. If n equals to 3 or if n equals to 2, what happens? Let us see what happens over here. I will just add n over here or twice over here for n equal to 2 and 3 for n equal to 3. Now in this case what can happen is, instead of reacting with another molecule of same kind, what it can do is this oxygen can directly attack this own carbon, that is form a kind of ring. So if this oxygen with a lone pair of electron, which is a nucleophile, and Br is a leaving group, attacks this carbon, then this Br leaves and we have a cyclic kind of structure, and that structure will actually be something like this, because we have 1, 2, 3, 4, 5 membered ring, and here also there is a 5 membered ring with a oxygen in one of the elements. So that means this option is also correct. And similarly, if n equals to 3, we will have a 6 membered ring with oxygen in the middle, and again this option is correct. So what do you learn from this? We learn that for nucleophilic substitution reactions, you do not need an extra nucleophile. Just take this molecule, add some base, you can have intermolecular nuclear reactions, intermolecular nucleophilic reactions, and you can have intramolecular nucleophilic reactions. Clearly, intermolecular and intramolecular, the meaning is, in this case, when n is equal to 1, what we get is that this reacts with another molecule of the same kind. That is kind of an intermolecular nuclear reaction, nucleophilic reaction. That is, it is happening between two different molecules. They combine with each other by a substitution reaction. That is, the O minus attacks the carbon of the other molecule and this Br leaves. But what is intramolecular reaction? The intramolecular reaction is this kind of reaction or this kind of reaction where a stable ring is forming. Now you can immediately ask a question, for n equal to 1, why didn't I write the intramolecular product? In that case also, this O minus can directly come and attack this carbon and the Br can leave. But why didn't I write it? It is the same reason why the cyclization of a compound occurs. The cyclization of a compound can occur only if the number of carbons in the ring is at least 5 or 6. 6 is the better number because that removes the strain from the molecule. So at least a 5 carbon membered ring should be forming, otherwise the cyclization in the molecule will not happen. So this was a nice question which is based on the SNI. We have read SN1, we have read SN2, and this is another nucleophilic substitution which is SNI. Not very different from SN2 because here just the intramolecular group attacks another group and that group leaves. So it is intramolecular. So we have discussed E1, E2, even CB, even conjugate base, SN1, SN2 and SNI, or the nucleophilic substitution intramolecular or intermolecular. Fine. Let us now do a match the following. So enough of multi-correct, single correct, subjective questions. Now let us do a match the following. In match the following, there are 4 questions, there are 4 options, and you are supposed to choose one of them, or you are supposed to match one by one. It can have multiple answers also, that is, one question can have more than one answers. I can easily explain you. Match. We have 4 questions and we will be having 4 options also. So let me give you the options first. The options are 312 and the numbers is 1.0. Why is it the 4th one? It should be 2nd. 1.0. The 3rd option says 0.8 and the 4th option says 0.4. 0.4. Now, I will give you 4 questions over here. You have to match one by one. The questions are, if we consider this molecule a benzene ring, NO2 and X over here. Now, if X is first option fluoride, second option chloride, third option bromine, fourth option iodide. So if X is this, then match the reactivity over here, or to, in a better way, a relative reactivity. So we have the questions that if this is a compound and if X is fluorine, chlorine, bromine, iodine, then the relative reactivity of this compound is so and so. So you have to match this with these 4 options. So first of all thing, relative reactivity means it must be undergoing some reaction. What is the reaction that this compound can undergo? Let us try to find out. This is a benzene ring with a NO2 group and a halide group, and this reminds me of nucleophilic aromatic substitution. When a NO2 group is present, that means the bimolecular displacement mechanism. What is that bimolecular displacement mechanism? That is, if some another group Z comes over here and then the carbon ion rotates in the benzene ring, it is delocalized in the benzene ring, a sigma complex is forming, and we get a stabilized carbon ion, and then finally this X will leave. So that means the slowest step in the reaction is if nucleophilic aromatic substitution, or in short NAS. In NAS, the slowest step is what? The slowest step is the formation of carbon ion. We have X, we have Z, and we have NO2. So this is the most slowest step, carbon ion, carbon ion. From here, this is the RDS, and this is also the rate determining step. We know that in a reaction the slowest step is the rate determining step. I have explained it to you a lot of times, I will not explain it again. So we know this is the RDS. So that means the relative reaction rate definitely depends on this step. That is, the stability of this intermediate determines what will be the relative reactivities of these compounds when X is F, Cl, Br and I. Now I have told you that the slowest step is this, but generally what mistake student does is X is there and nucleophilic aromatic substitution. Nucleophilic substitution means X must be a good leaving group, correct? Yes, agreed, X must be a good leaving group, but it is in SN2 case where the slowest step is the leaving of the halide, or in SN1 case where the formation of carbocation or leaving of the halide is a slowest step. Yes, so the good livability group, good livability criteria is a very important thing, but not over here, because here the first step is the formation of carbon ion and not the leaving of X group. Leaving of X group is the slowest step in case of SN1 and in case of SN2, and we know that F is the worst leaving group, and hence you will definitely mark F as 0.4, Cl as 0.8, Br as 1.0 and I as 312. But actually the order is just the reverse. Just the reverse of whatever the order is for the normal SN1 and SN2 cases. Because here the stability of carbon ion is the slowest step, formation of carbon ion is the slowest step, and hence the factors which stabilize this carbon ion will be the better ones. And we know that fluorine is having more electronegativity, and hence this would stabilize the carbon ion more as compared to Cl, as compared to Br or even iodine. So the reaction order is like this. Fluorine is having more electronegativity, and hence it can stabilize the carbon ion more, and the bromine can even stabilize the carbon ion more as compared to the iodine. And hence the correct options are, for the first one first, second one second, third one third, and fourth one fourth. That is, iodine is lowest, bromine is next, fluorine is next, and chlorine is next, and fluorine is the highest. And you see the difference between the relative rates, it is quite high. That is because of the electronegativity difference between fluorine and chlorine. So this is a very nice question because the relative rates depend on the slowest step of the reaction. And if you know the mechanism of the reaction correctly, then only you can answer this question. Otherwise, you will definitely make the mistake which I have just now explained you. So a nice match the following. Let us move on to the next one. Now the next one is an interesting subjective question. So let us see what the next question has in store for us. So you see, all the questions that we have discussed have got very cute, nice logics and very simple logics. I mean, the previous question, minus the following, was very nice. The previous to that, intermolecular substitution. It is such a simple concept. You know, it is quite evident when you see the question. It must be something of that sort. You will get the feeling, but still we will be scared and we will mostly mark none of the above. At least I would have marked none of the above if I was reading the question first time in the question paper. So that is why you have to be calm in the examination. You have to think in all possible ways that why is the product not, which I am thinking is not there in the options. So think in the manner, and definitely an IIT will force you to think in that manner and you will get the answer. So the question is expected products. See, it is expected products. Expected products for E2 and SN2 mechanism for the following reactant. So the reactant is, we have a cyclohexene ring. In that we have some groups attached with some specific stereochemistry. So let me draw the specific stereochemistry. Till the time you revise what are the stereochemical aspects of SN2 and E2 reactions. So this is CH3 and this is Br. This is hydrogen here, hydrogen, then we have CH3 and we have hydrogen over here, CH3 and we have hydrogen this way. Fine. So this is our reactant and our reagent is NaOCH3. Fine. And there is a solvent also, CH3OH. Now, what are the possible products in case of E2 and SN2 mechanism? Here you have been given the mechanism, that means no need to worry which mechanism to follow, just you have to follow the correct mechanism, the correct steps in the mechanism, that's all. First, let us go for E2. E2 is a elimination bimolecular mechanism. In that, the first step is, there is only one step in that mechanism, the breakage of Br bond and the breakage of this bond clearly, and there is a hydrogen abstraction by a base. Now, what is the base over here? The base is CH3O-. And the most important part is that both hydrogen and Br should be anti-coplanar, but coplanar. And clearly, if this is the Br which is away from us, and this hydrogen and this Br on the same side, you see this hydrogen is on the top and this Br also is on the top. So that means this H and this Br cannot eliminate. That cannot undergo the dehydrohalogenation process. That means E2 is not possible with this hydrogen and this Br. So we have to go for the next carbon. This carbon, yes, there is a hydrogen present which is actually down. So the Br is up and the H is down. So they are anti, but you have to make sure that they are coplanar also. And in fact they will be coplanar. Why? Because these two carbon bonds are in plane, these two carbon bonds are in plane. So what happens is when it is down and when this is down, so this is kind of an eclipsed conformation. This hydrogen and this hydrogen, the bonds are eclipsed, and this CH3 and this Br, the CCH3 bond and CBr bond, they are eclipsed. So what happens is this becomes exactly in plane with this. You can also show it this way. This comes like this, and this goes something like this, and this goes something like the outside thing, which goes something like this. So now this hydrogen and this Br come in plane, and this bromine is up and this hydrogen is down. So they are also anti to each other, and hence we do get E2 mechanism, but with only this hydrogen. So now only one hydrogen is there, so only one product is possible, and you need not have to see any stability criteria also, because there is only one product possible. The correct stereochemistry is followed by only one product, and that is this product with CH3. Now CH3 has become planar and hydrogen this way, and there is a CH3. This stereochemistry you have to mention, this is behind and this hydrogen is towards us, because this stereochemistry will not be changed because of the reaction over here. The stereochemistry of these two carbons have changed, they have become now planar. So that was the E2 product, and that is the only product, so no need to apply any stability criteria over here. Let us go for the SN2 mechanism. So now SN2 mechanism, what is the requirement? The requirement is that this nucleophile should be small enough to be approachable to this carbon, and after the reaction there is a stereochemical change, that is the configuration of this carbon reverses and nothing happens to the configuration of the other two carbons. So now we have a small nucleophile, we have not so much overcrowding, also a little bit of overcrowding is there, and hence this CH3 can attack this bromine. But now there is one more trick in this question. The inversion in configuration occurs if and only if this CH3 can attack the bromine from the back. But now this CH3 OCH3 minus, this OCH3 minus will attack this carbon only from the same side as that of Br. It cannot attack from the back side because of the presence of the ring, and hence here there is no inversion of configuration, and you get the same product. For only difference is this Br is replaced by OCH3. So you see how many logics are involved in each and every question. There is one small logic, and if you don't crack that logic at that time, that's all, your question is gone. One part of the question might be correct, the other is just simply gone. Your logic should be the ring is preventing this nucleophile from coming and attacking from the back, and that is why it has to attack from the same side, and that is why there is no inversion of configuration, but there is the retention of configuration. Fine. Let us move on to another nice question. The question says we have to choose from one of the four options. So it is actually a single correct option. So the question is this: there is a ring and there is actually a bridged ring, and we have a Cl over here. Now this on reaction with OCH3 minus gives you what? The four options are reaction through SN1. The option 2 is reaction through SN2. Third option says reaction through SNI, and the fourth option says reaction through SN. There is no reaction. There is no reaction. Fine. So out of the four options, which is correct? Now first of all think, what is the possible reaction over here? Here we have got an alkyl halide and we have got a nucleophile. So what do you think is a possible reaction? Clearly it has to be a nucleophilic substitution reaction, and the three options are given to you, whether it is SN1, whether it is SN2, or it is the internuclear or intermolecular nucleophilic substitution. So tell me which one is correct, whether SN1 is correct or SN2 is correct or SNI is correct. In fact, here if you go for SN1, you get a carbocation over here which is very unstable, because this bridged compound is not a planar compound. Here the bridged is, this ring is in the plane, but the bridged atom is somewhere over here, and this angle is not 120 degrees, so that carbocation does not remain a planar carbocation, and hence the SN1 mechanism is not possible because of the very unstable carbocation. What about SN2? Yeah, SN2, the requirement is that the nucleophile should be able to approach this carbon so that this halogen can go away. But what happens here is the bridge again prevents the nucleophile to come and attack it. So again there is no reaction through SN2. And SNI, there is no meaning in this because there is no nucleophile present already in the ring. So that means that actually there is no reaction. But it is no reaction is the correct answer. So a very nice question to show you that not if there is alkyl halide and there is a nucleophile doesn't mean that the reaction will happen. And even if the reaction happens, the quantity will be around 0.0001%, not more than that. So that is the question. A single correct nice question based on the conditions, proper conditions for the requirements of these nucleophilic substitution reactions. What are the requirements for SN1, what are the requirements for SN2, and what are the requirements for the SNI reactions. So let us move on to the next question. The next question is a comprehension. So the comprehension says something about Grignard reagents. Comprehension. Now, the first question says Grignard reagents generally occur in dry ether because your first option is the stronger acid diethyl ether will displace the weaker acid RH from its salt. That is, the stronger acid diethyl ether will displace the weaker RH from its salt. This is the first option. The next option says the stronger acid H2O will displace the weaker acid RH from its salt. So instead of diethyl ether, we just have H2O. The meaning of these statements I am going to explain you, so don't worry if you are not able to follow what these statements mean. The third statement says that water slows down the reaction. Wonderful statement. Water slows down the reaction. The fourth statement says water mixes with ether, preventing ether to perform its function. Water mixes with ether, preventing it from performing its function. Now, these are the four options given to you, and you have to tell the correct reason for the given question. Grignard reagent occurs in dry ether because. Now, why do you think the Grignard reagent occurs in dry ether? We have discussed this and we got to the conclusion that if we use H2O, then what happens is the Grignard reagent will be destroyed. Or in other words, the stronger acid H2O acts as an acid, will displace the weaker RH from its salt. The RH is nothing but R minus, the salt of RH is nothing but R minus, and hence it is right that the H2O will displace the H and will come something like this and destroy the reagent. But diethyl ether does not have the proton or does not have the acidic proton to do so, and these two options are totally nonsense. Water slows down the reaction. How can water slow down the reaction? I mean, the formation of Grignard reagent is a nucleophilic substitution, and water in fact supports the reaction if it is a nucleophilic substitution. So this is wrong, and even water mixes with ether to prevent its performing its function is also a very wrong statement. So the correct statement is the second option, that the stronger acid H2O displaces the weaker acid RH from its salt. The second question on this comprehension is, Grignard reagent can't be prepared from OHBr, first option. Second option says Cl. Third option says Cl. Fourth option says we have dichlorobenzene. Cl and Cl. Now, Grignard reagent can't be prepared from which one of these? Clearly, one thing we can say that Grignard reagent can definitely be prepared from this because it is an alkyl halide, and it is a characteristic reaction of alkyl halide that Grignard reagent is prepared from it. What about the other three? This is an aromatic halide, and as we have seen that even aromatic halides we can prepare the Grignard reagents. That is, this with Mg ether gives you MgCl. So this also is very possible reaction, and if this is possible, this is definitely possible. So the only option left is this. And yes, we have just now seen why the Grignard reagent can't be prepared from this. Because if you take the carbon ion over here, then it can attack the hydrogen of some other molecule, and the Grignard reagent would be destroyed. So the correct option is the first one, and that was our question. A very simple question, but the logic here is you should not get confused between this and this option. That you can think that aromatic halides cannot give you Grignard reagents, so that means there are multiple correct options. Actually they are not, the only first option was incorrect or correct. So let us go to the next question of the comprehension, which is the last question of the comprehension. The third question says that the function of tetrahydrofuran in the preparation of Grignard reagent is, first one acts as a solvent, second one it helps in maintaining the reactivity of magnesium, C both, and D none of the above. So now, what is this tetrahydrofuran? Tetrahydrofuran is this compound. It is a 5-membered ring with one atom replacing by oxygen. So this is tetrahydrofuran, a 5-membered ring with one of the this is a 4-membered ring. 5-membered ring would be this way. So now this is THF, and this also comes in the hydroboration oxidation. If you remember, we use BH3THF as the reagent. Now this is a non-polar reagent, I mean not so much polar. This is something like an ether itself, but the only difference is this is a cyclic ether, and we use generally the diether or diethyl ether. Fine. What is the role of this ether? Definitely it acts as a solvent, because it needs a solvent. Grignard reagent, the preparation needs a solvent. Now, what about this? It helps in maintaining the reactivity of magnesium. How does it help in maintaining the reactivity of magnesium? Now, the thing is, if we are using a polar solvent, then in that case, the magnesium reactivity is reduced due to solvation. And since this is a non-polar solvent, this does not solvate the Mg2 plus and it maintains the reactivity of Mg2 plus, and hence the role played by tetrahydrofuran is both as a solvent and maintaining the reactivity. Fine. So this was some facts about Grignard reagent which can easily be logically deduced, but this was a nice comprehension to give us some detail about it. So let us consider the final question of the lecture. It is a mechanism reaction. You have to tell me what is the mechanism of the reaction and what is the final product. Now the question is, there is an aromatic halide Br and the reagent given to you is FeBr3. That's all. This is the question. You have to tell me what is the product of the reaction and you have to give a proper logical explanation or mechanism. So aromatic halide with FeBr3. Aromatic halides, the reactions we have considered: nucleophilic aromatic substitution, electrophilic aromatic substitution, and Fittig reaction, and even you have the Grignard reagent preparation. Now this reaction falls into which category? That is the first question. It clearly does not fall in the category of Grignard reagent preparation, nor even the Fittig reaction. So this has to be either a nucleophilic aromatic substitution or a electrophilic aromatic substitution. So in order to determine whether it is nucleophilic aromatic substitution or electrophilic aromatic substitution, you need to first find out what is this molecule, whether it is a nucleophile or whether it is an electrophile. And in fact, this is a catalyst. It is neither electrophile and nor a nucleophile. And I think I made a mistake over here. This is CH3. Now, this is neither an electrophile and nor a nucleophile. This is a catalyst which can act as an electrophile. How does it act as an electrophile? Because it has got empty d orbitals. So apparently this does not seem to be either a nucleophile nor electrophile, just a normal Fe compound, but it can act as an electrophile because of the empty d orbitals. So we have got an electrophile, we have got a benzene ring. So let us start the reaction. So the reaction is the mechanism, proper mechanism, and for mechanism you need to write the full structure here: CH3, now FeBr3, FeBr3. What happens in the first step of the electrophilic aromatic substitution? The first step is the donation of the electron density from the benzene ring to the Fe atom. So suppose we start from here, then what happens is that the positive charge comes over here. That is, the negative charge comes over here and this goes to the electrophile. So we write it like benzene ring, then we have positive charge here, CH3, and our electrophile as Fe, it's right, negative, and this has FeBr3, but then this will get a negative charge and hence one of the bromines would leave to give FeBr2. Fine. So do you understand why does one of the bromines leave? Because the carbon has donated a lone pair of electrons into the Fe empty d orbitals, and hence one of the Fe and Br bond has to be broken. So at this step we get a Br minus. Fine. What is next here? Next, what should happen is the stabilization of the carbocation. Yes, the carbocation is quite very much stabilized, and here it is here and then it goes over here, but we see one thing, that this is going only in the meta position, and yes, that is correct because this is having a positive inductive effect. That means it supplies electron density, or kind of does not supply electron density, because inductive effect is not shifting, it is just pushing the electrons, you can say. And this is sp2 carbon and this is CH3, so the electron density would be this way only. So it is supplying electron density. So at the ortho and the para positions you would have only the bromines, only the positive charges, and hence it is stable. So next is what? What is the next step in these reactions? So the next step is the attack of Br minus over the benzene ring. And if you attack this Br minus over the benzene ring, you will get, let me redraw the structure, you will get two isomers of CH3 and Br plus CH3Br. This is the ortho isomer, this is the para isomer, and there is a 50-50% chance that these two will be produced. And this reaction has a name. It is called the Friedel-Crafts reaction. So we see we can produce substituted aromatic halides using Friedel-Crafts reaction. What we need for a Friedel-Crafts reaction is a catalyst, electrophilic catalyst, for example AlCl3, FeBr3, no problem, and we need a methyl group so that can act, and any activating group that can act as a ortho-para directing group, and there we have the Friedel-Crafts reaction. Now this CH3 can be replaced by several groups, for example OH, COH, and even NO2. Activating groups definitely increase the activity of the benzene ring, especially OCH3. This increases the activity of the benzene ring immensely, and the reaction is very fast, this Friedel-Crafts reaction. But what happens if you put NO2 on a benzene ring? It is observed that we know that the reactivity would decrease because the Friedel-Crafts reaction requires an activating group so that it can supply the electron density to the benzene ring because of the formation of the positive charge, while NO2 deactivates the benzene ring, that is, it takes away the electron density from the benzene ring, and hence this will slow down the reaction. And in fact, it is observed that this slows down the reaction 1,000,000 times. So this is almost unreactive. Nitrobenzene is almost unreactive towards Friedel-Crafts reaction. So you see the effect of ortho-para directing and the meta-directing groups in electrophilic aromatic substitution, and we have seen a nice Friedel-Crafts reaction. So that's it in this lecture. This was the last question of the lecture. I hope you have liked the logics and the cute logics, simple and cute logics which we have used in all the questions here, and please go through them once again so that it becomes more clear to you. I hope you have liked my lecture. Thank you.